We will talk about the Faraday's law, which is the third law in the Maxwell equation. And of course, we'll also talk about Lenz's law. Lenz's law is only the negative sign in the Faraday's law. Yeah, so, and then we will talk about the inductor, inductance, and the self-induction, RL circuit. Maybe I will just slightly skip it. After finish chapter 30, I will talk about how to solve the RLC circuit generally. And before that, I will tell you how to teach you how to solve ordinary differential equation, which is useful for the circuit. Yeah. So here we will talk about the Faraday's law and Lenz's law. So this is the first experiment. So as you can see here, so this one hold a magnetic bar, and then this is a coil. This is a coil, and then this is just a amperemeter, or ammeter, which means it is just to measure how much current going through this loop. There's no supply there, so which means if there is nothing else, there shouldn't be any current going through this loop. But here for this experiment, this one, we have the ampere loop, amperemeter setting here for this loop, and then this one hold a magnetic bar, and then if it move closer to this loop, then the ammeter tells you that there is some current going through this loop, which is the induction current. So a conducting loop is connected to a sensitive ammeter. It's like ammeter. Sensitive means it can send some very small current. So because there is no battery or no other source of EMF induced, there is no current in the circuit originally. If there is no this magnetic bar, then there shouldn't be any current. However, if we move a bar magnet toward the loop, a current suddenly appears in the loop. The current disappears when the magnet stop moving. Even the magnet bar is hold there, then there still be no current. As long as the magnetic bar is moving, then there will be current. So if we then move the magnet away, a current again suddenly appears, but now in the opposite direction. Which means maybe if the guy put the magnet closer to it, then let me see, increasing the, yeah. So if the magnet is moved closer to the loop, then like this direction, then the induced current will be clockwise. And then if it stops, then there is no current. And if we move the current backward, then the current will be counterclockwise. So this is So if we experiment for a while, we would discover the following facts. So a current appears only if there is a relative motion between the loop. Between the loop and the magnet, which means that if you just hold the magnet there, and then if you move the coil closer to the magnet, then there will still be current. So it depends on the relative motion. So one must move relative to the other. If they move together without changing the relative position, then there is still no induction current. So when the relative motion between them cease, so faster motion of the magnet produce greater current. If moving the magnet north pole towards the loop cause, say, clockwise current, moving the north pole away cause counterclockwise current, I just mentioned. And if you move the south pole toward or away from the loop, also cause the current, but in the reverse direction from the north pole effect. So whether you use a north pole to move into the loop or you use a south pole, then the induced current will be in the opposite direction. So it depends on the speed of the motion and also the polarity of the magnetic bar, and also the relative direction of the motion. So here we have a second experiment. We replace the magnetic bar by another loop and also the battery here. So in previous chapter we know that this is a magnetic dipole, and actually this loop with a current is also a magnetic dipole. And I suppose you should know that this is mu equals NIA. If there is one loop, N equals 1, I is the current going through this loop, area is A is the area of this loop. I suppose you have already studied that because you have midterm exam tomorrow. Okay, so for this experiment, we use the apparatus, which means the equipment with the two conducting loop close to each other but not touching. If we close switch S, close means connect these two points, which means close, or just put it there is close. Close the switch to turn a current in the right hand loop. Then actually this is the positive side, so the current will go in this direction. So an induced current in the left hand loop. So the ammeter suddenly and briefly register a current and in the left hand loop, which means if you switch this loop on, switch it on, or short this circuit, then suddenly there will be an induced current on this loop. If the switch remains closed, no further current is observed. So it only appears for a short while, and then there will be no current again. If we then open the switch, another sudden and brief induced current appear in the left hand, but in the opposite direction, which is somehow like this case. You move it closer to move the magnetic part closer to the loop, and then there will be current. And then if you stop, there will be no current. And then you remove it, there will be current, but in the opposite direction. This is a similar case. So we get an induced current only when the current in the right hand loop is changing, either turning on or turning off, and not when it is constant, which means keep or switching on or keep switching off, then there will be no induced current. The induced EMF and induced current in this experiment are apparently a cause when something changes. But what is that something? Faraday knew. So so Faraday realized that an EMF means is the short form of electromotive force. in Chinese it is called 电动式 electromotive force EMF, and the current can be induced in a loop, as in our two experiments, by changing the amount of magnetic field and passing through the loop. He further realized that the amount of magnetic field can be visualized in terms of a magnetic field line passing through the loop. So here we define magnetic flux phi b to be this surface integral. So in chapter 23, you all already know this is the net flux of the electric field. Here we don't have this circle because we don't consider a closed surface. So we only consider maybe for this case this area. So it is not a closed surface. So here we only use this normal integration sign and then b dot dA, which means we count for the magnetic flux. This is the magnetic flux density. So we integrate it over the area, which is the total flux through this area, through this loop. So this is the phi b, and where the integral is taken over the area, the SI unit of the magnetic flux is called Weber, which is Tm square. T is the SI unit for the B field, and area, of course, meter square. So if B is perpendicular to the area and uniform over it, then this is nothing but B times A. So you just integrate the constant over the whole area. So this is simplified to this one. Okay, up till now, any questions? So the magnitude of the EMF induced in a conducting loop is equal to the rate at which the magnetic flux phi b through that loop change with time. And this is called the Faraday's law. So with the notion of the magnetic flux, so magnetic flux is defined like this. Actually, you can calculate it yourself, and we can state Faraday's law in a more quantitative way and useful way to be like this. So we take the derivative of the magnetic flux with respect to time, and then with a minus sign, then it is the induced EMF, induced electromotive force for this secondary loop. If there is n coils or n turns for the secondary coil, then we multiply a n here on the right side. So this will be one of the form of the Faraday's law. So this is actually the Faraday's law. So the induced EMF tends to opposite the flux change, and the minus sign indicate this opposition. So this minus sign is referred to Lenz's law. So the whole equation is called the Faraday's law. But at that time, Lenz only find this negative sign, and this negative sign is called the Lenz's law. It's called the Lenz's law. So it is like I think more than 100 years ago, or at least 150 years ago, maybe more than that. So yeah, so this minus sign is called the Lenz's law, and maybe later we will have more discussion about the Lenz's law. But before that, we will have a let's see a sample problem first. So here, the long solenoid S, which is the blue one is the long solenoid, has 220 turns per centimeter and carry a current I. Its diameter D is 3.2 centimeter. At this center, we place a 130 turn closed packed coil, which is the orange one, of the diameter D. Of course, you can see it is a bit smaller. So the current in the solenoid is reduced to 0 at a steady rate in 25 milliseconds. What is the magnitude of the EMF that is induced in the coil C while the current in the solenoid is changing? So yeah, so it tells you that it is originally 1.5 ampere, and it reduced in a steady rate in 25 milliseconds. So in 25 milliseconds it reduced to 0. So so here we can see phi B is B times A, because within a solenoid we assume the magnetic field is uniform. So the magnetic flux is simplified to just a multiplication. So B is mu 0 I small n for the B, and then times A. So mu 0 is 4 pi times 10 to minus 7, and then A is 1.5, and then N is 220 per centimeter, but we actually need to change it to 22000 turns per meter. So we need to multiply 100 to this number. So it is 22,000. And then the area for the smaller one would be pi 0.021 over 2 square. We will consider the smaller one, because when we consider the induced current for the coil C, we of course consider the cross-section area for this one, not the larger one. Because originally we have a current going through the big coil, and then it induced the current in the smaller one. So we consider the cross-section area for coil C. So it is 1.44 times 10 to minus 15 Weber. So in this case, as long as the current will be reduced in a steady rate, so in this case, phi B also reduced to 0 with a steady rate, which means d phi B dt equals minus 1.44 times 10 to minus 5th power over 25 times 10 to minus 3rd power, because it takes 25 milliseconds to reduce to 0. So this is the I, it will reduce like this. And likewise for the phi B, from 1.44 times 10 to minus 5 Weber. And it takes 25 milliseconds to reduce to 0. So this is actually the rate of change. So this value is minus 5.76 times 10 to minus 4th power Weber per second. And and finally we can use the Faraday's law. So the electromotive force is minus n d phi b dt. So it has 130 turns. So it is 130 times 5.76 times 10 to minus 4th power. So it is 75 millivolt. It is not a large voltage. Any questions? Okay, if no questions.